Convoy escorts encountered the same operational failure repeatedly. A submarine appeared clearly on sonar equipment. The escort ship immediately began the attack approach. Range closed steadily toward the submerged contact. Then, sonar suddenly lost the target. The submarine had not disappeared. The attacking ship caused the problem itself. Propeller turbulence disrupted sonar echoes completely. Acoustic returns vanished during the final seconds. The submarine turned away beneath the blind zone. Depth charges detonated behind empty water. Operational reports recorded this failure again and again. Admiralty engineers studied the attack geometry closely. They concluded the weapon method was fundamentally flawed. A new system had to strike before passing overhead. That solution became the Hedgehog. Royal Navy escort doctrine revealed severe anti-submarine limitations. Convoy protection required reliable submarine destruction methods. The standard depth charge attacks created persistent tactical disadvantage. Attacking destroyers had to pass directly above submarines. Sonar contact collapsed during final attack approach. Propeller cavitation masked acoustic echoes completely. Sonar operators lost target bearing within final seconds. Submarine commanders exploited this predictable vulnerability. Hard rudder turns allowed rapid lateral escape. Depth charge patterns frequently detonated behind empty water. Admiralty operational research documented repeated engagement failures. Escort commanders requested forward-delivered explosive solutions. Admiralty engineering committees opened experimental weapon studies. Directorate of Miscellaneous Weapons Development assumed technical responsibility. Initial design concept used a spigot mortar architecture. Spigot systems eliminated conventional recoil absorption requirements. Projectile propulsion originated from internal ignition cartridges. Launch rods remained fixed within reinforced steel sockets. Bomb tail assemblies contained propellant impulse chambers. Ignition drove projectiles forward along steel rods. This mechanism avoided heavy gun recoil assemblies. Simplified construction suited rapid wartime manufacturing demands. Early prototypes tested within controlled coastal proving ranges. Experimental launch racks carried small projectile numbers initially. Testing officers evaluated projectile trajectory stability carefully. Aerodynamic fins attempted to stabilize forward flight. Early bombs tumbled unpredictably during ballistic travel. Engineers increased fin surface area gradually. Modified tail units corrected mid-flight yaw deviations. Projectile bodies measured approximately 7 inches diameter. Total loaded projectile mass approached 65 pounds. Warhead filling used Torpex explosive mixture. Torpex contained RDX, TNT, and powdered aluminum. The mixture produced stronger underwater shock waves. Shock pressure improved structural damage against submarine hull plating. Engineers required precise impact. Fuse sensitivity calibration. Depth charge weapons detonated through hydrostatic pressure triggers. The Hedgehog system required direct hull collision. Missed projectiles remained inert after water entry. No explosion occurred without physical impact contact. This characteristic preserved sonar clarity after missed attacks. Depth charge blasts previously obscured sonar tracking entirely. Maintaining sonar contact became the central tactical objective. Engineering teams expanded launcher capacity significantly. Final launcher assembly carried 24 spigot rods, spigots arranged within rectangular welded steel frames. The frame mounted above reinforced forecastle deck structures. Naval architects studied deck stress distribution carefully. Structural reinforcements strengthened bow plating beneath launchers. Launcher assembly weighed nearly 1,000 pounds. Weight distribution affected ship trim calculations slightly. Ballast adjustments compensated forward weight concentration. Projectile pattern geometry required precise dispersion angles. 24 bombs formed an elliptical impact field. The strike zone extended roughly 40 feet diameter. Forward projection distance approached 250 meters. This allowed attacks before the ship passed overhead. Sonar operators maintained constant acoustic contact throughout approach. Range estimation determined correct firing moment. Bridge officers maintained stable heading during attack run. Fire control required coordinated communication between departments. Sonar operators reported range continuously. Bridge officers corrected course deviations carefully. Weapon officer armed firing circuits before launch. A single switch triggered simultaneous ignition cartridges. Electrical firing circuits linked each spigot rod. The copper wiring carried ignition current through sealed conduits. Saltwater exposure threatened electrical reliability frequently. Technicians improved insulation using rubberized sheathing. Continuity. Checks occurred before every convoy patrol. Misfires occasionally resulted from broken wiring connections. Safety investigations revised inspection procedures afterward. Projectile storage lockers installed near launcher assemblies. Each locker held one complete firing pattern set. Additional ammunition stored deeper inside escort vessels. Handling crews transported bombs using canvas lifting straps. Fuse protection caps remained installed during storage. Crew removed caps immediately before loading procedures. Premature fuse exposure risked accidental detonation. Loading crews worked methodically along spigot rows. Bomb tail tubes slid over each launch rod. Gravity held projectiles upright before firing. Full reload required approximately 3 minutes initially. Experienced crews reduced reload time through drilling practice. Training manuals standardized loading sequences precisely. Weather conditions complicated deck handling procedures. Heavy seas increased projectile dropping hazards. Safety helmets became mandatory during loading operations. Engineering trials continued aboard escort corvettes. Testing involved submerged steel target frames. Targets anchored beneath controlled test waters. Observers recorded projectile impact distribution patterns. Initial tests revealed pattern drift problems. Ship roll altered launch angles unpredictably. Engineers considered mechanical stabilization devices briefly. Complex stabilization systems proved unsuitable for escorts. Operational doctrine instead emphasized early firing timing. Crews fired slightly before calculated range closures. This compensated forward ship momentum effects. Repeated training gradually improved accuracy levels. Operational deployment began during late 1942. Atlantic convoy escorts received first production installations. German U-boat activity remained intense during this period. Escort commanders quickly evaluated new weapon effectiveness. Initial patrol reports showed inconsistent results. Crews misjudged firing range frequently. Some attacks produced no detonations whatsoever. Admiralty training schools introduced specialized instruction courses. Simulated submarine targets improved crew proficiency. Attack run drills emphasized sonar communication, discipline. Training reduced tactical confusion during engagements. Subsequent patrol reports documented improved hit probability. Statistical analysis confirmed greater submarine destruction rates. Submarine commanders reported sudden, unexplained forward explosions. Hedgehog attacks often struck before evasive maneuvers completed. Hull impacts created localized structural fractures. Pressure waves entered internal compartments rapidly. Flooding sometimes forced submarines to surface immediately. Escort ships confirmed kills through oil slick observations. Floating debris occasionally appeared after detonations. Operational research departments compiled engagement statistics. Comparisons showed higher success than depth charges alone. Escort groups integrated Hedgehog weapons widely thereafter. Destroyers required modified deck foundations for installation. Some vessels lacked sufficient forecastle clearance. Naval architects redesigned mounting brackets accordingly. Additional reinforcement plates strengthened destroyer bow decks. Fleet refits installed launchers across multiple ship classes. Manufacturing plants expanded production capacity rapidly. Launcher frames fabricated through welded steel sections. Spigot rods machined from hardened alloy steel. Precision machining ensured correct rod alignment. Quality inspectors rejected rods with minor deviations. Propellant cartridges manufactured at naval ammunition factories. Cartridge ignition required consistent pressure output. Faulty cartridges sometimes produced incomplete launches. Several misfire incidents triggered safety investigations. Admiralty engineering boards revised cartridge tolerances. Revised cartridges improved launch reliability significantly. Explosive warheads filled inside secure ordnance facilities. Torpex casting required controlled temperature conditions. Cooling rates affected explosive density uniformity. Technicians monitored batch density carefully. Completed bombs packed within reinforced wooden crates. Convoy supply depots distributed ammunition to escort bases. Logistics planners tracked monthly consumption rates. Atlantic convoy battles increased ammunition demand sharply. Factories raised production quotas accordingly. Escort vessels often sailed with hundreds of projectiles. Operational commanders expressed increasing confidence in Hedgehog capability. U-boat losses rose gradually through 1943. Improved radar detection also supported escort operations. Air patrol coordination expanded submarine hunting coverage. Despite these improvements, Hedgehog remained primary attack weapon. Forward attack geometry fundamentally changed engagement tactics. Submarines faced shorter reaction windows during detection. Maintaining sonar contact denied underwater escape opportunities. The weapon required careful crew coordination. However, Inexperienced crews occasionally fired outside effective range. Poorly timed launches wasted ammunition supplies. Continuous training remained essential for success. Operational research continued evaluating performance characteristics. Mathematical modeling examined projectile dispersion mathematics. Wind direction occasionally altered ballistic trajectory slightly. The crosswinds shifted pattern impact positions laterally. Fire control corrections compensated predictable drift. Heavy seas introduced additional instability factors. Ship pitching altered launch rod orientation angles. Experienced crews adapted through earlier firing commands. Post-war analysis reviewed the system's engineering limitations. Manual reload procedures slowed repeated firing cycles. Future anti-submarine weapons explored automated loading concepts. While the later Squid mortar incorporated hydrostatic detonation mechanisms. Hydrostatic triggers allowed lethal near-miss detonations. Hedgehog bombs still required direct impact. Contact. However, the system avoided dangerous, friendly blast effects. Escort ships rarely suffered self-inflicted damage. Operational safety remained comparatively high. Mechanical simplicity aided reliability under harsh sea conditions. Maintenance demands stayed manageable for small escort crews. Naval historians later recognized Hedgehog's strategic influence. Forward-throwing mortars reshaped anti-submarine warfare doctrine.